Swayam Prabha. Digital India. Educated India.
Good morning. Welcome to the fluid mechanics class. Today we are in the fourth lecture of fluid dynamics. We have already covered the Reynolds transfer theorem. We have seen the linear momentum equation. We have also discussed the equation of motion for real as well as ideal fluids, and we have seen the applications of all these concepts. And then we have derived the Bernoulli's equation from the Euler's equation, and we have seen the combined application of energy equation as well as linear momentum equation. And today we will see some of the applications in terms of measurements of flow rate through pipes. Okay. So those equipments or measurement devices that are used in pipe flows to measure the flow rate, how they are using these principles or the Bernoulli's equation, and they are being used to obtain the flow rates. So in this case, so most of the times what we do, we take the pressure difference. So basically by changing some kind of flow path, we change the pressure, and by changing the pressure, if you change the flow path, you basically change the velocity, and by changing the velocity from the Bernoulli's equation, we know you basically change the pressure. So once you change the pressure, you measure the pressure at two locations and find out what are the velocities, and then from that you can find out what is the flow rate. Okay. So in measurements of flow rate through pipe, the flow rate is usually measured by providing some coaxial area contraction. So you basically reduce the area through which the flow is taking place. So by doing that, you generate a pressure difference, and that pressure difference is obtained, or that pressure difference is measured, and that's how we can find out the flow rate. All right. So therefore, determination of flow rate from measurement of pressure drop depends on straightforward application of Bernoulli's equation, which we know. Okay, the Bernoulli's equation links the pressure, velocity, and datum head. So assuming that datum head, let us say same or it could be different, but we can find out what is the velocity by measuring the pressures. Okay. So there are various devices which operate on these principles. We will discuss two of them which are widely used. One is venturimeter, the other one is orifice meter. Nozzle is also going to operate based on the similar principle, but we will, in this class, we will mostly focus on these two devices. One is venturimeter, another is orifice meter. Okay. So now let us look at the venturimeter. If you look at the venturimeter, this is a typical venturimeter that you can see in the figure. Okay. Now in this, the section that is starting from here is the start of the venturimeter, and then this is the end of the venturimeter. If you look at this venturimeter, which is used for measuring the flow in pipes, okay, it has three sections. First one is a convergent section that you see from here. The section is converging, or the area is reducing up to a distance this. So this section is called convergent section. Okay, and then you have a throat here. Then there is a divergent section, and again the flow is expanding, and again the area is increasing, and you got to this point. So now the area or the inlet portion of this convergent section should be same diameter of the pipe. Then only you can attach that. And again the end portion of the divergent section should also have the same diameter of the pipe, so that you can fit in a section of the pipe and connect it in between, so that you can measure the flow. All right. Now the convergence is short while the divergence is slightly longer, or the convergence is shorter or it is rapid, whereas the divergence section is given as a gradual variation. Why is it so? When the flow is converging, it is most likely that it will still attach to the flow boundary or the surface boundary. So it will not detach from the surface boundary. If it don't detach from the surface boundary, then you will not have the turbulence effect. You will not have a lot of loss that will actually will be encountered due to this turbulence or flow separation, which we will study the flow separation later, but at least we will say that the flow will not detach from the surface. Now in case of divergent section, if you suddenly expand it, which we have seen in the sudden expansion, that if you actually increase rapidly, then there is a possibility of flow separation or the flow might detach from the boundary. In that case, the losses are going to be very large. So in order to avoid the losses, the divergent section is gradual, okay, and the throat section is more of a constant cross section throughout, so that is called throat, okay. Now the meter must flow full, okay, the venturimeter or the pipe must flow full so that we can apply the Bernoulli's equation. If it is not flowing full, then you cannot apply the Bernoulli's equation, because it's going to be a kind of open channel flow condition. So we are not discussing or talking when the pipe is flowing full, okay. Now as I explained, the convergent section is shorter, and because the flow is going to attach to the surface, the losses are going to be small, and through the throat there is no variation. And once the divergent section is gradual, there also the losses are going to be minimum. So overall the losses are considered to be very small, okay. So now because of this, the losses are small and it is very convenient. So this kind of device or the venturimeter is widely adopted for various industrial applications as well as various flow measurement applications. Let us say you have the city water pipes where you are supplying the water to a residential community or to the city, and you want to find out how much water is really flowing. You let us say want to measure how much water is flowing, and based on that you want to charge, or you want to ensure that the required amount of water or the demand is really supplied from the source. So you need to understand that. So to do that, you can apply or you can use this kind of venturimeters and put it, and the sizes of these venturimeters can really vary from very small to very large. We'll see that it can vary from few centimeters to few meters, okay. So now this venturimeter, if you look at, is always used in a way, as I said, it has to be used in a way that the convergent section is facing the upstream and divergent section is in the downstream, or the shorter portion is towards the upstream side and the longer portion is towards the downstream side. If you use the other way around, then the purpose why it has been designed like that is going to be defeated. So that sometimes by mistake somebody is not aware of that, it is our job to identify and ensure that it is installed correctly. All right. Now this ensures a rapid convergence passage and a gradual diverging passage in the direction of the flow to avoid losses of energy due to separation, as I said, okay. Or it should not detach, it should not create any kind of turbulence inside to generate losses, okay. Now in course of a flow, the converging part, the velocity is going to increase as the area is reducing. We know from our continuity equation from conservation of mass, if your area is reducing, the velocity is going to increase, okay. And similarly, when the area is increasing in the divergent section, the velocity is going to gradually reduce from the throat to the divergent section, okay. So velocity from here, from the section 1 will keep on increasing up to section 2, and again from this section 2 till the end of the divergent section, the velocity is going to decrease. Now when we are telling that the velocity is going to vary, if we look at the Bernoulli's equation, there is a direct relation of the velocity with the pressure. So the moment the velocity is increasing, please remember, when there is an increase in the velocity, the pressure is decreasing. That we have already seen, right? And the same thing is also observed here. So now if you see, the pressure is going to be higher at the section 1 compared to the section 2, isn't it? Because the velocity is lower at 1 compared to the section 2. The pressure is going to be just the opposite, okay. Now if you look at that in this manometer, U-tube manometer that has been attached to this, which is one end of that U-tube is attached to the pipe and the other end of the U-tube is attached to the throat, because we know exactly what is the cross-sectional area of the pipe and we know exactly what is the cross-sectional area of this throat. There is no variation, so there is no problem of exactly finding out the values. So these two are the points where the U-tube manometer can be attached. Now once it is attached, we know that the pressure at this location 1 is higher compared to location 2. So if the pressure is higher, what will happen? This will push the manometric liquid down and the manometric liquid will rise up on the section 2. So we will get a difference, overall difference of head of the manometric liquid. Let us say in this case, if it is mercury, then there will be a head of mercury that you will observe. Okay. So the velocity reaches its maximum value and the pressure reaches its minimum value at the throat. Now, in venturimeter, you can find out that a decrease in the velocity and increase in the pressure takes place in course of the flow through the divergent section. Okay, but we are not really measuring that, but we know that it's going to happen. Okay, so but our point of measurements are only the initial pipe and the throat of the venturimeter. We are trying to find out the pressure difference, and from that we will try to find out how we can get the discharge through the venturimeter. All right. So now to get that, we have these two sections. We have already understood that there is a energy which is going to remain same at both the sections. The overall energy is going to remain same, and we have already said that the losses are going to be very, very small. Assuming that the losses are really small, we can now equate the energy, total energy at these two locations by applying Bernoulli's equation. So if you apply the Bernoulli's equation, you can write down that P1 by gamma plus V1 square by 2G plus Z1. Assuming this Z1 is here, which may be same on both sides, but right now let us write the full equation. So plus Z1 is equals to the total energy here at section 2. What is that? The pressure component due to the pressure is P2 by gamma plus V2 square by 2G plus Z2, and losses are neglected. Okay. So now this is our Bernoulli's equation applied to these two sections. All right. Now if we rewrite this equation, just rearrange, we can write down V2 square by 2G minus V1 square by 2G is equals to P1 by gamma plus Z1 minus P2 by gamma Z2. Okay. So basically, you know already the hydraulic gradient, that is P1 by gamma plus Z1 minus the hydraulic gradient at section 2, P2 by gamma plus Z2. If we take this difference, let us say this difference is the delta H in terms of head difference. Okay, what we are writing here is the pressure head, velocity head and atom head. So here we are taking the pressure head and atom head at section 1 and section 2. This difference is, let us say, delta H. Okay, and that is nothing but equals to V2 square by 2G minus V1 square by 2G. Now if we just rearrange this again, this V2 square by 2G minus V1 square by 2G, we can write down by taking V2 square by 2G common, or taking it out, we can rephrase this whole thing. And now if you look at this equation, it is V1 by V2 whole square, and this V1 by V2, if we apply the continuity equation, we don't know the velocities. Okay, please remember that velocities are unknown for us. We have only measured the pressure difference between these two sections. So that is, let us say, delta H. Okay, so we don't know the velocity. Now we have to represent these velocities in terms of some known parameter. What are the known parameters? The area of the pipe and the area of the throat are known. So this is, let us say, A1 and A2. By applying our continuity equation, because the flow is considered as incompressible, you can apply the continuity equation, which is A1 V1 equals to A2 V2. By applying that equation, now you can write down this V2 square by 2G multiplied by 1 minus A2 by A1 square, right? Now this equation is going to be useful. Here we have seen V2 square by 2G, okay, is equals to this. Now I can write down this component V2 square by 2G 1 minus A2 by A1 whole square is equals to delta H. Okay. So now if I write down that, I can rephrase the whole thing for calculating V2. If you see in the previous slide that here you have only one unknown, that is V2, and A2 is known, A1 is known, delta H is going to be measured, so everything else is known. So from there we can just write down V2 is equals to square root 2g delta H. This delta H is nothing but the head that is measured here. I will come to that head little bit later, but before that let us see this equation. So we can write down this divided by square root 1 minus A2 by A1 whole square. Now if I just take this out, I can rephrase this equation like this: A1 multiplied by square root 2g delta H divided by A1 square A2 square. Okay. Now here the delta H is the head difference. This head difference is of mercury. But what is our actual working fluid? That is possibly different, right? It is not going to be the same as the manometric fluid. So we have to calculate the delta H in terms of the working fluid. Okay. So once you calculate that delta H in terms of working fluid, that will be substituted here and you will be able to get the value of the velocity. Okay. So finally, the discharge can be calculated. How do you calculate the discharge? It is nothing but A2 V2, because we are calculating V2 here, we will multiply the area at 2. So by taking that A2 V2, we can find out the discharge. It is theoretical discharge. Why theoretical? Because we have neglected the losses. We have not considered the losses in this. We have assumed that the losses are small and we have neglected. So theoretically, this is the value we could get. And if I write down that A2 multiplied by V2, I can rewrite the above equation by taking A2 into that. And this term, which is nothing but just a constant for us, for one particular system, it is going to be a constant. So I can find out and let us say denote it as K. So this K root over delta H is going to give you the value of the discharge. So for a system, for a particular venturimeter and pipe system, you know what is the value of K that can be obtained prior to the flow measurement. Now, if you know the K, you just have to measure the value of delta H, substitute and find out the theoretical discharge. Now, if in a laboratory we measure and find out what is the actual discharge through the pipe, the flow that is coming out, we can find out what is the actual discharge. We will collect in a container and we will see what is the volume that is collected in a given time, and from that we can find out what is the discharge that is coming in terms of meter cube per second, right? Once we find out that discharge, that is going to be my actual discharge, and I can calculate what is my theoretical discharge and I can find out what is the actual discharge. The ratio between these two is going to give me the coefficient of discharge. That is basically a correcting or correction factor that you multiply with the theoretical discharge to get the actual discharge. Now anyone should be able to tell that whether the actual discharge is going to be more or the theoretical discharge is going to be more. Now in case of actual discharge, we know that it is multiplied with CD. Q theoretical is multiplied with CD to get the actual discharge. So the actual discharge can never be more than the theoretical discharge. It can only be less. Okay. So the value of CD has to be less than 1, or in a idealistic condition it can be equal to 1, but usually there will be losses for real fluid. Losses might be very small. Okay. So due to the losses, there will be some reduction in the discharge. So actual discharge is going to be less than the theoretical discharge. All right. So CD value is going to be less than 1. And if you see, the value of CD for venturimeter is mostly going to vary in a range of 0.95 to 0.98. So that itself says that the losses are less than 5%. Okay, which is very small. And that is why this device is widely adopted in many applications. Okay. So there are a couple of advantages of the venturimeter. If we look at the simple, it is very simple, it's reliable, and it's suitable for a great range of pipe diameters. As I said, it can vary from very small 5 centimeters to even 6 meters. So large industrial applications if you go to the right now, possibly it may not be possible, but if you see some kind of pipelines that are supplying water to a city, those pipes are going to be much bigger, which could be of the order of 3 meters, 4 meters, 5 meters, and so on. And these venturi meters can be attached to that, and the flow can be measured. So the application is quite wide, and without calibration, the discharge may be predicted within very small range. That's the error could be minimized up to 1% or 1.5%, which we have seen that the CD could go up to 98% or 0.98. So the calibration, without calibration also, this is going to be very accurate. Overall losses do not exist, do not exceed more than 10 to 15%. So that we have seen that the losses are going to be very small. In worst case also, it cannot exceed this amount. Okay. So the large discharge can be handled because it can be used for large diameter pipes. All right. And regardless of the orientation of the venturimeter. So whether you keep the venturimeter straight or the horizontal, or you put it or install it at an angle that is inclined. There may be a piping system which may be going with some inclination, and you install it, still it is dependent only on the pressure difference, gauge difference that is measured. How is it? We will see in an example problem. Okay. So now the venturimeter, we have, let us now look at a example problem. So the example problem here says you have a venturimeter with an entrance diameter of 0.3 meter and a throat diameter of 0.2 meter, and that is used to measure a volume of gas, okay, that's flowing through the pipe. The discharge coefficient of the venturimeter, that is CD, is given as 0.96. Now assume that the specific weight of the gas as 19.62 Newton per meter cube. Okay, so specific weight means gamma or rho g, that is given, rho g of the gas is given as 19.62 Newton per meter cube. Calculate the volume flowing when the pressure difference between the entrance, that is at section 1, okay, and the throat, that is section 2. So at the entrance and the throat, the pressure difference is measured, and that is found out to be 6 centimeter. Okay. So now if it is 6 centimeter of water, okay, so the manometric fluid used here is water, and there is a flow of gas in the pipe and venturimeter. All right. So for this, we have to find out what is the discharge. Now I can straight away go and use the formulation that I have derived and find out the answer. Now let us say somebody doesn't really remember or doesn't want to remember what are those formulations. Why unnecessarily I should remember? All right. So apply the basic concepts, which is the straightforward application. Okay. So let us start applying the basic concept and solve this problem. What are the parameters that are given? We know the unit weight is given. Okay. So that is nothing but your gamma g, rho g. Rho g subscript is basically for the gas, and multiplied with the gravitational acceleration. So rho g is 19.62 Newton per meter cube. CD is the drag coefficient, that's given 0.96. D1 the diameter of the pipe, that is, or at the entrance, that is given as 0.3 meter, and the diameter at the throat is given as 0.2 meter. Okay. So with these parameters, now if we want to find out the discharge, what we need to know what is the differential pressure. Okay. Now the differential pressure is already given as 6 centimeter, but let us not take that as such. Let us find out what will be the pressure at this location. If I draw a line, we know that in a continuous fluid at 2 points that are in the same elevation, the pressure is going to be same, and by applying that concept, we can say that the pressure here and pressure here are going to be same. So now let us say this point, I will equate all the pressures that are acting. So if I equate that, I can write down that P1 plus P1 is the pressure here at point 1, let us say that is at the center line, okay, plus rho g Z1, let us say the distance from here to here is Z1, okay. So I can write down P1 plus rho g Z1, alright. Similarly, if I want to find out the pressure at this location P2, this location, then I can write down all the pressures acting over this. So the pressure at this center line is P2, alright. Then I can find out the pressure that is acting due to the gas that is standing over this location. So that is nothing but rho g, that is the gas density, multiplied by g multiplied by Z2 minus h. So now let us say this height is my h, okay. So from here to here it is h. Now the distance all the way from this point to this point, let us say Z2. So basically Z1 and Z2 are the elevations from a reference. So let us say this is my datum. So this Z1 and Z2 are nothing but my datum head. Alright. So by taking that, I can write down rho g multiplied by g Z2 minus h is due to the gas. Then due to the water, that is manometric fluid, I have the pressure that is exerted by this cross section, that is this zone, okay. So that is going to be rho w g h, okay. H is the head of water that is measured in this manometric U-tube manometer, okay. So now once we have written this, let us now rephrase this equation. If I want to write down the pressure difference between these 2 points, I can write down P1 minus P2 will be equals to rho g g multiplied by Z2 minus h. Then this term will come, this is going to be rho wg into g. Then this term will come to the other side with negative sign, that is going to be here. Alright. Now if we take the z terms and h terms separate, then we can write down the gamma g or unit specific weight of gas multiplied by this difference Z2 minus Z1 plus the density difference. If you look at this, this is rho w and this is rho g. So multiplied by gh, okay. So that is going to give you the total pressure difference. Alright. Now if we just write down this again, this term what we have written, we know this, okay. 1000 is rho w, 1.225 is the density of, let us say, air, okay. But in this case the gas density can be found out. I think here I have used the density of air, but one can find out what is the density of gas, and if you find out, it could be approximately 9.62, so it will be actually 2. So now if it is 2, then you can take this and this will be 998, okay, multiplied by gh, okay. So now by using this, you will get approximately 587.88. There is not going to be much of a difference. All right. So this term, which is already given, 19.62 multiplied by Z2 minus Z1 is going to remain. So P1 minus P2 is given by this expression. Now let us apply the Bernoulli's equation. Okay. So this is just the pressure difference at these 2 points that we have obtained. Now let us apply the Bernoulli's equation between section 1 and 2.